So far, we've been mostly focused on addition, and that makes sense because addition is the most fundamental of all the operations, right? Addition means continue to count 1 star, 2 stars, 3 stars, plus 1 more. Now we have 4 stars, right? Counting sheep in a field. That's where math really first started. But in order to deal with sign numbers or non-whole numbers, non-integers like 2/3 or 0.07, it's actually more helpful to think of it as continue to move, right? 3 places to the right and 1 more to the right to get 4. Or 3 to the right and then 1 to the left, or 3 to the right and then 2/3 to the right, or whatever numbers we're using here, moving on the number line still helpful, right? So we've got 2 different basic definitions of addition, and when we recognize move includes both an amount, how long the arrow is, and a direction, whether it's going to the right or the left. That longer definition I gave you before is the better, most precise one. This is kind of the crux of it. All right, but now we're going to move on to another operation that is slightly more interesting. Multiplication actually has 3 definitions. The first one is probably the one you're thinking of if you're trying to think of the definition, and that is repeated addition. Okay, so I'll give the other definitions and then we'll get into how these relate to each other, how 3 definitions can all apply to the same operation, and then we'll look at that. So dilation or contraction, and then change units or dimensions. So if we look at a multiplication problem like 3 times 5, let me write this on here. How much is 3 times 5? Right? Well, we could say 3 times 5 means I have 3 5s. That's 5 plus another 5 plus another 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we get to 15. That's the idea of multiplication, meaning repeated addition. But that's hard to deal with when I say something like 2/3 times 5. How do I add 5 2/3 of the time? Do I mean something like take my 5 and get rid of this third? That doesn't really work. That's not quite a number. Do I have to switch that around to 5 2/3? It seems a bit like cheating. We'll talk about why multiplication is commutative in just a moment. But that's not going to work if I do 2/3 times 4/7. Right? How do I write 2/3 4/7 of a time? Right? We need some other way to understand multiplication beyond just repeated addition. And that's where dilation or contraction come into play. If I'm looking at the number line, and I've got 5 on there, so here's 0, here, oops, here's 0, and here's 5. When I multiply that by 3, I'm making it 3 times bigger. I'm dilating it. I'm stretching it out to 3 times its normal size. It's not so much that I'm taking this arrow exactly 3 times, though since 3 is a whole number, that's what I'm doing. But I'm stretching it out to 3 times its size. That lets me deal with fractions, where I can take 5 and squeeze it in, contract it, so that it's only 2/3 its size. And whatever that value is, if I take this 5-foot long stick and cut it into 3 equal pieces, that's going to be the value. Right? And since we haven't talked about fractions just yet, I won't explain why that would be 10/3 or 3 1/3. We'll learn about that in a couple more videos. But the idea is contraction multiplying by something less than 1 is squeezing it to a smaller version. And dilation, just like your pupils dilate when you're scared or in a dark room or when you're at the doctor's office and they put those drops in to dilate your eyes. Right? Dilation means get bigger. It's expanding the size of it. So that could have been 3.1 times 5. We're still expanding it by a little bit more in that case, not by 3, but by 3.1 times the size. The definition still holds. Now this third definition is going to help us understand the properties of multiplication and really key us into how to deal with word problems. Right? If we're creating models of unfamiliar real world situations, we need to be able to deal with situations that are more than just I have 3 bushels and 5 apples in each bushel. How many apples do I have? Right? 5 apples here, 5 apples here, 5 apples here. How many apples is that? I can count them all together. I have 15 apples. There's a word problem. Repeated addition, fine. But where we really deal with multiplication in word problems tends to be with units involved. So let's say I have an index card that's 3 inches by 5 inches. What would that look like? Well, maybe it looks like this. I could use my straight line tool, but this is faster. Or it might look like this. For that matter, you don't have to hold pieces of paper straight up and down like this or like this, right? Maybe it's at some funky angle. Going off my page here. Right? It's the same index card. Doesn't matter how I put it. The area of that index card is the same. If I split this into squares, each 1 inch wide, 3 gives me 1, 2, 3. 5, I need to separate that up. So I guess I should go 1, 2, 3. 1, 2, 3, 4, 5. I want to know how many of these squares are in this shape. Well, I've got 1, 2, 3, 4, 5 squares across there. Another 5 here. Another 5 here. I could put my apples the same way. If I'm counting my apples, I could say I've got 5 apples in the first basket, another 5 in the second basket, another 5 in the third basket. it can make that picture, and maybe that'll make it faster to say 5, 10, 15 apples, but I'm still counting individual pieces here. One apple might be a little bit larger than the next one. Right? Apples aren't all exactly the same size or the same weight. Um, if one has a chunk eaten out of it by some worm or one of my children, it's still an apple. I'm not counting two half apples as a single apple, right? These are just 15 apples. Here, if this last inch is a little bit less than a whole inch, then it doesn't count as 3 inches, right? I'm not just counting discrete squares, I'm counting up the entire area of the whole rectangle. That's not me scratching out, that's me shading in. And area is a fundamentally different unit than length. I'm not counting inches going along this direction, then going along this direction, then going along this direction, then going along this direction. That's perimeter. Area is saying 3 inches times 5 inches. 3 times 5, we already, from our first definition, 3 fives is 15. 3 times 5 is 15. But my units are now inches times inches. That's inches squared. 15 square inches. So you can say the area is 15 square inches, whether we write it out in words or using the notation there. Okay? That's how we deal with change of units or dimensions. In this case, we went from 1 dimension length to 2 dimensions area. Changing units, that's how we deal with distance equals rate times time, right? Miles per hour times hours gives you miles. Miles is a different unit than miles per hour or than hours. Um, Force equals mass times acceleration, right? Kilograms, meters per second squared, two completely different units measuring how heavy something is, measuring how fast something's accelerating. Put those two different units together, and you get this brand new thing called force, a different unit, whether we call it kilogram meters per second squared, or we call it newtons, or we use some other unit depending on what units we're using to measure these two quantities. Right? We're getting something fundamentally different by multiplying. Multiplication does not follow all the same rules as addition, especially when it comes to units. Right? That's also going to help us when we deal with sign numbers in our next video.